Hi, everyone. Thanks for coming. My name is Jerry. This is Brandon. We're both software engineers here at Phaidra. So Phaedra's mission is to make the industrial sector radically more resource efficient. And it's doing this by building a virtual plant operator. This is essentially an autonomous agent that acts as a control system for physical facilities. And the goal is to be able to adapt to changing conditions in these facilities over time. Typically, a lot of these facilities are controlled using hard-coded controls logic. These are built based on assumptions that don't hold over time. So equipment gets changed in and out, the environment changes, and systems degrade, and thus the original control systems don't always work well. Phaedra's control system is meant to learn from the data over time so it can adapt to these changing conditions and actually improve. And some of the systems that we're actually live in production in include data centers, pharmaceutical manufacturing facilities, as well as district energy. The way that I like to think about deploying one of these agents to a facility like this is in two stages. One is actually setting up the problem itself, and then setting up the solution for the problem. So the problems that we solve are sequential decision-making problems, where every few timestamps you'll want to make a decision based on the observations that you make on the facility. So the components of this problem include what the action space is. In our case, this could be turning on and off chillers at a chiller plant, opening and closing valves for a pipe full of water. The observations would include various sensor measurements at these facilities like temperature, pressure, humidity, and virtual sensors of equipment status and such. And of course, we'll have an objective which oftentimes is minimizing resource usage, such as energy. On top of all that, we also have to deal with constraints on the system. Of course, the most resource efficient way to run a data center is to shut everything off, but we can't just do everything so blindly. In order to build this, the agent every few seconds will observe data from these facilities, run a search algorithm to figure out what the best action is to minimize the objective, and then send those actions to the facility. The agent itself is made of a pretty sophisticated search algorithm, but internally it requires a model of the future. Essentially, this model is an action value function that takes the current observations as well as some potential candidate actions and tries to predict what the future outcome will be. And the rest of this talk, we'll talk about the data processing pipeline for building this model. So the data that we receive can come from the customer in many different ways. It could be live streamed from the data through our own APIs, but it could also be bulk historical imports of previous data. So one example of that is CSV files that the customer can give to us. These are files of where the rows are tuples of timestamp, sensor name, and the actual measurement value of those sensors. So there's several stages that we have to transform this data in, and I'll just briefly cover some of them. One is we have to pivot the data from this tuple form into a matrix where every row is a timestamp and a column is a sensor value. This requires us to clean up the data, make sure the timestamps are aligned, properly formatted, as well as figure out what to do with dupes, as well as missing data. Another important part of data processing is actually standardizing data into a representation that kind of abstracts away the dirtiness of the real world, effectively. Everybody may have a different way of putting units for their data. They may have different sampling frequencies. They may have different naming conventions. But we want to build a representation for an agent that's kind of agnostic to all that, so that the same agent can work for multiple types of systems of the similar type. From this standardized data, we then need to build training data for the models. Since we're building predictive models of the future, typically, we will take windows of these observations. As inputs, we will look at the actions and the state in the beginning of the window, and for the targets, we try to predict what will happen throughout the period of the window itself. So originally, these scripts were built using ad hoc Python scripts and Colab Jupyter notebooks. This was kind of out of necessity as we were building proof of concepts and iterating a lot of different concepts and features. But of course, this doesn't scale. And as soon as we started deploying this to production systems and had to replicate this in multiple customers, we needed a better solution than that. Some of the problems that we ran into were running out of memory. We had to constantly try to fetch bigger and bigger machines. And these jobs would take a really long time to run, sometimes tens of hours for one of these pipelines. And sometimes they will fail at the 11th hour, sometimes literally, and you have to go through all the logs and try to debug what's going on. After several consideration, using the Ray core framework was really appealing to us because it allowed us to move from our ad hoc scripts to this distributed engine very easily. Theoretically, moving processing from single process to this distributed computation should be very difficult, but Ray's primitives of actors and tasks made that pretty easy for us. We were able to really easily parallelize a lot of these tasks and got the runtime from tens of hours to just under 1 hour. We're also able to replicate the same pipeline to many different facilities through purely a configuration-driven approach. And there's a bunch of debugging, tracing tools that Ray provides for us to make actually analyzing this and improving it much easier. So Ray has significantly improved our data processing infrastructure, but it isn't without its challenges. So I'll hand over to Brandon to talk about some of those challenges and what we did to solve them.
Thank you, Jerry. So I want to start with sort of the biggest challenge we faced, which was solving the multi-tenancy problem. So our data processing platform needs to be able to support running multiple jobs for multiple users. And when we initially built this platform, we started off with a single cluster approach, so all jobs getting submitted to a single cluster. But that has a couple of problems. You could run into resource starvation issues where jobs might be competing for resources and could even end up deadlocking each other and then no jobs ever finish. And then if you're running into memory issues on like unexpected memory usage with some of your rate tests, you might end up killing workers and as a result, killing other jobs that might be running on those same workers. So what we did, we built a job system which instead of running everything on one cluster, we spin up ephemeral clusters to run those jobs. We're leveraging Kubernetes under the hood to manage all the cluster lifecycle magic. And as you can see in the diagram here, how it works is users submit their jobs, they go onto a queue, and then the queues only pop jobs off once we can guarantee that there's enough free capacity to guarantee that those jobs will be able to run to completion. So that solves the deadlocking issue. And then we create the Ray jobs, submit them to the cluster, and then since we have a lot of jobs running, we have a lot of Ray dashboards, obviously, so users can access those dashboards via a reverse web proxy. And if you look at the diagram, there's actually multiple job queues. The reason for that is because we have a way of defining job configurations where if we have different types of jobs, we might want isolated queues to have isolated resource capacities. So for example, as Jerry mentioned, we have raw data and tag data processing jobs. So instead of saying, oh, we want to have a max capacity of 10 jobs, for example, running, if users submitted 10 raw data processing jobs, then we wouldn't be able to run any tag data processing jobs. And that's something we wanted to avoid. So instead, we can define job configurations for the different job types we have and say, for example, oh, we want 5 and 5 of each job type as the max capacity. And then if you exceed the capacity for one job type, you can still submit other job types. Something else you could do with these job configurations is define job sizes. So if you have a rate task which is running on a custom tag data processor resource, you could then say, okay, I want medium jobs that use this resource to use some standard nodes, and then large jobs are going to use high memory nodes. So this allows us to do dynamic resource allocation. And then finally, since obviously these clusters are getting spun down once the job is complete, we need to export all the logs out of the clusters so that users can debug afterwards. So we're using some neat Ray features to make that simpler in our Ray scripts. So we're setting up some IDs to uniquely identify the jobs and using the worker process setup hook, which automatically just runs some logging setup functions to add these IDs to all the logs emitted by all the Ray tasks from that job. Going over some performance improvements we were able to make to the jobs. Obviously, the job lifecycle sort of system is only one half of the equation. You actually want the jobs themselves to also perform well. So as Jerry mentioned, we have different types of data. We have raw data, which is the customer sensor data, and then we have tag data, which is our internal standard representation. So this expression at the top is an example of what a definition for a tag might look like. So we might say something like a certain time window of sensor values for sensor A, the mean of that is going to be one tag. And then, so in our live stream pipeline, where we're just ingesting raw data in real time, we're pretty much always computing just one timestamp of tag data because we're just receiving that data, 24/7. So when we first designed our data processing jobs, we just took our existing live stream logic and just put it into a for loop and iterated over the entire data set. And the way you can make that more efficient is just having small batch sizes and running a lot of those in parallel. But that's going to be fast, but it's not going to be resource efficient, right? So you just want to make use of vectorization here. So that's an example of how you might transform that expression into one that makes use of vectorized operations. And then another example of a performance improvement we made to the jobs is more intelligent task pipelining. So this piece of code is a high level of what our agent deployment job might look like. So we need to process the tag data, write it to the database. Then we process our feature data, write that to the database. And once the feature data is in the database, we can go ahead and trigger the model training. Now, if we pay attention, the feature data processing is taking the tag data as a reference. And so that means we don't actually need the tag data to be available in the database. So what we can do here is just completely remove the blocking call, which waits for the tag data to be written to the database, and just shift that to the bottom. And the reason this is a performance improvement is because the tag data, since it represents all of the raw customer data that's coming in, that's a much, much greater volume of data than the feature data. So the database writes for that take a lot longer than the feature data writes. So by the time we hit the model training, we're still going to be writing tag data to the database, but that's okay because the model training doesn't require the tag data. It only requires the features, which have already been computed from the tag data. So yeah, those are some of the challenges we faced and some of the improvements. Now our platform is in a much better spot than it was, when we first started this work, but there's still some more improvements we can make. So there's improvements we can make with regards to surfacing issues and errors in the jobs for users. So I mentioned already that we're exporting all the logs from the jobs so that users can debug the jobs to see why one might have failed. But we can further improve this by having the jobs kind of self-report why they failed, and then having the user clients just pull that information so that users don't even have to look at logs. We can also break up our array jobs further. So there's going to be use case in the future for us where we might want to just trigger certain parts of our pipeline. So for example, we might want to trigger just the feature data processing on an existing tag data set. And so since we now have all these array scripts, which are just a bunch of array tasks, we can just import them into a new job and easily create these new job pipelines. And finally, we can move some of our other use cases which aren't currently using array to leverage the power of array. So our agent inference is getting quite complex. So that's something that in the future we might want to actually move to array. But yeah, with that, that's it. Thank you for listening.